Hello students, in earlier classes we have understood about carbohydrates and proteins, which are two major nutrients that are supplied through the diet for purposes of maintaining the health and well-being of a human being and all living systems too. In today's class we will understand about lipids, which is the chemical name of fats and oils. The objectives of today's class is to enable you all to understand the definition of lipids, to get acquainted with the classification and properties of fatty acids as well as fats, and also to get acquainted with different types of phospholipids and non-phosphorylated lipids. To introduce lipids, they are biological compounds whose chemistry involves a diverse group of compounds, the common and defining feature of all these compounds being their insoluble in water and solubility in all organic solvents. The biological functions of lipids are as diverse as their organisms and their structures. The fats and oils are the principal stored forms of energy in the human body because they give 9 kilocalories per gram oxidized. Phospholipids and sterols are major structural elements of the biological membranes of all cells. And other lipids, although present in relatively smaller quantities, play crucial roles like enzyme cofactors, electron carriers, lipid absorbing pigments like chlorophyll and carotenoids, hydrophobic anchors for proteins, chaperones to help membrane proteins fold, emulsifying agents in the digestive tract, hormones and intracellular messengers. To define lipids, it is customary to say in terms of their solubility in certain organic solvents such as ether and chloroform, the presence of esterified fatty acids and their utilizability by living organisms. Definition of lipids is more functional and operational, so it can be loosely defined as any of a group of organic compounds that are insoluble in water, but soluble in organic solvents. Now, we come to the classification of lipids. Just like carbohydrates and proteins, you have different kinds of lipids which can be classified based on either their physical properties at room temperature, whether they are solid or liquid, or on their polarity, whether they are soluble in water or organic solvents, and based on their essentiality or need for humans. But the preferable classification is based on their structure. So, based on the structure, they can be classified into three major groups as simple lipids, complex lipids and derived lipids. So, if you look at simple lipids or neutral lipids, examples are fats and oils, that is the regular fat or oil that is consumed by a human being through their diets, and waxes which are present in certain plants, which coat the plants, fruits, vegetables and give them their shiny appearance. Compound lipids are non-phosphorylated, example glycolipids, proteolipids, sulfolipids, sphingolipids and lipoproteins. The phosphorylated compound lipids include glycerophospholipids and sphingospholipids. Among the derived lipids are sterols, chlorophyll, carotenoids, cholesterol and various hormones. So, you look at the storage lipids or the simple lipids. The fats and oils used almost universally as the stored forms of energy in living organisms are derivatives of two types of compounds called fatty acids and glycerol. Hence, they are called triacyl glycerols or triglycerides. One glycerol molecule having 3 carbons is attached to 3 fatty acids on each of its carbon. The fatty acids are called hydrocarbon derivatives because they have both carbon and hydrogen, and they are at a low oxidative state. The cellular oxidation of fatty acids to carbon dioxide and water, like the controlled rapid burning of fossil fuels in internal combustion engines, is highly exergonic, releasing large amounts of energy. The types of fatty acids that can be esterified to a glycerol molecule can be divided into saturated fatty acids, unsaturated fatty acids, short chain fatty acids and long chain fatty acids. Fatty acids start with 4 carbons and can go on to more than 30 carbons. The saturated fatty acids have a carboxyl group COOH on one end and a methyl group CH3 on the other end, with CH2 molecules in between forming a hydrocarbon chain. There are no double bonds in saturated fatty acids. In unsaturated fatty acids, 2 hydrogens from adjacent CH2 molecules are removed to form a CH double bond CH, which is the principal defining factor of an unsaturated fatty acid. Then short chain can be those which have less than 10 carbons and long chain can be those which have more than 18 carbons. Medium chain can be those between 10 and 16 carbons. The structure of fatty acids, as I have already just mentioned, they have a carboxyl group COOH or COO minus in the charged form on one end and a methyl group CH3 on the other end, with the hydrocarbon chain, that is CH2 molecules, joined together in between. These fatty acids can be straight if they are saturated, or they can have a kink or a twist if they are unsaturated. At the double bond, they can turn into a kind of a kinked tail that can be shown in the figure presented here. So, fatty acids are defined as carboxylic acids because they have a COOH group ranging from 4 to 36 carbons. So, they can be called as C4 to C36, C indicating carbon. C2 to C26 exists in plants, and above that the larger fatty acids or the longer chain fatty acids are present in waxes. In some fatty acids, this chain is unbranched and fully saturated, as it has already been described, having no double bonds. In others, the chain contains one or more double bonds. If it has one double bond, you can call it monoanoic, 2 double bonds dianoic, 3 double bonds trianoic, more than 3 double bonds, it can be called a polyanoic fatty acid. A few contain 3 carbon rings, hydroxyl groups or methyl group branches. These are unusual fatty acids, not normally present in the foods that we generally eat. So, the general formula of a saturated fatty acid is CnH2nO2. So, if it has n number of carbons, it has twice the number of hydrogens, and uniformly all fatty acids contain 2 oxygens. The unsaturated fatty acids are CnH2n minus 1 O2, minus 1 because 1 hydrogen is removed from 1 CH2. There is a nomenclature to refer to these fatty acids. A simplified nomenclature for these compounds specifies the chain length like C4, C6, C8 etc., denoting that it contains 4 carbons, 6 carbons, 8 carbons, and this is separated by a colon, and if there is a double bond, the number of double bonds is indicated. For example, 18,0 is a saturated fatty acid with 18 carbons. 18:1 is an unsaturated fatty acid with 1 double bond. The position of any double bond is specified by a superscript number. For example, 18:1 delta 9, delta meaning double bond, 9 meaning the position of the double bond, the carbon on which the double bond is present. And the most commonly occurring fatty acids have even numbers of carbon atoms. Very rarely do you come across odd numbered carbon atoms in plants or in the diet. So, these are some examples of saturated fatty acid. Butyric acid, the name has been derived from butter having 4 carbons. So, it is called C4:0, caproic acid C6, caprylic acid C8, capric acid C10, lauric acid C12, myristic acid C14, palmitic acid C16, stearic acid C18, arachidic acid C20 with no double bonds, behenic acid C22. So, people who have familiarized themselves with lipids are familiar with this nomenclature in the sense that if we say C16, we immediately know it is palmitic acid. So, you do not need to define a fatty acid with its name, just giving the nomenclature of the number of carbons is sufficient. If you look at the commonly occurring unsaturated fatty acids, you have myristolic acid C14:1 indicating 14 carbons and 1 double bond, palmitolic acid 16:1, oleic acid 18:1, the most commonly occurring fatty acid in all plants or plant related fats, linoleic acid C18:2, another commonly occurring fatty acid in plant based fats, alpha linolenic acid 18:3, arachidonic acid 24, eicosapentaenoic acid 25, erucic acid 22:1, docosahexaenoic acid 22:6. Eicosapentaenoic and docosahexaenoic acid are commonly occurring in fish and fish oils, and they are very good for health, indicating that they have the capacity to lower the blood cholesterol levels. Then you have another type of fatty acids, the cis fatty acids and the trans fatty acids. If you look at the figure presented here, you will understand that a cis fatty acid has a kink. It twists itself around the double bond and the straight nature of the fatty acid is disrupted. So, it has a kink in its structure. These are the naturally occurring fatty acids, indicating that they are more flexible within the cell membrane. A cis configuration means that adjacent carbon atoms are on the same side of the double bond. You will understand this as I go along and show you the pictures. The rigidity of the double bond freezes its conformation, and in the case of the cis isomer causes the chain to bend and restricts the conformational freedom of the fatty acid. The more double bonds the chain has in the cis configuration, the less the flexibility. Now, with respect to trans fatty acids, if you look at the figure, it looks like a saturated fatty acid even though it has a double bond. A trans configuration by contrast means that the next two carbon atoms are bound to opposite sides of the double bond. As a result, they do not cause the chain to bend much and their shape is similar to a straight saturated fatty acid. This is what I was talking about. If you look at the two carbons and the double bond, both the hydrogens are on the right side and the long chains, the hydrocarbon chains are both on the left side. This is a cis configuration. This is a cis oleic acid 18:1. Its corresponding trans fatty acid is called Eliadic acid, where the two hydrogens are on the opposite sides and the two hydrocarbon chains too are on the opposite side. Now, in nearly all naturally occurring unsaturated fatty acids, the double bonds are in the cis configuration, as I already mentioned, and trans fatty acids are produced by fermentation in the rumen of epigastric animals or dairy animals and are obtained from dairy products and meat. They can also be chemically generated during a process of hydrogenation of unsaturated fats to produce saturated fats in order to improve their stability and shelf life. Now, fatty acids can also be divided into essential and non-essential fatty acids, meaning when you say essential fatty acid, it means that they cannot be synthesized in the body and they have to be provided through the diet. These are two types of fatty acid, 18:2 linoleic acid and 18:3 alpha linolenic acid. These cannot be synthesized under any conditions by an animal system or a living body. They can only be synthesized in the plants because the enzymes required for their synthesis are present only in the plants, and therefore, they have to be provided through the diet. All other fatty acids are called non-essential. It does not mean that they are not essential by the body, but it means that they can be synthesized in the body. Now, coming to physical properties of fats and oils, the non-polar hydrocarbon chain accounts for the poor solubility of fatty acids in water. So, the solubility is one physical property that is important. The longer the chain The fewer the double bonds, the lower is the solubility in water. Coming to the melting point, melting points are also strongly influenced by the length and degree of unsaturation. Double bonds cause lowering of the melting point, and cis fatty acids have lower melting point than trans. At room temperature at about 25 to 30 degrees centigrade, saturated fatty acids from 12 to 24 carbons have a waxy consistency, whereas unsaturated fatty acids of these chain lengths are oily liquids. This difference in melting point is due to different degrees of packing of the fatty acid molecules. Then boiling point increases with increased chain length. Coming to the reactions of fatty acids react just like any other carboxylic acid, which means that they can undergo esterification. Fatty acids can be reduced to yield fatty alcohols with CH2OH instead of COOH. Among the chemical properties, salt formation is important. For example, metals like sodium and potassium can esterify with a fatty acid to form RCOONA, R meaning the hydrocarbon chain, COONA is the COOH portion which esterifies with the sodium. The chlorine part of a sodium chloride joins with the hydrogen that is released to form HCl. Sulfated or sulfonated alkyl alcohols are produced on catalytic reduction. A fatty acid with reduction using hydrogen can become an alcohol or sulfated alcohol. These are highly efficient detergents or wetting agents, stable in acid and are not soluble if it is esterified with heavy salts like calcium and magnesium. This principle is used for preparation of soaps, detergents, etc. Ester formation. Esters are generally made by direct esterification with an alcohol in the presence of concentrated H2SO4 or anhydrous HCl. Interesterification is another property that refers to the formation of new esters when an ester reacts with an alcohol or an acid or other esters. Some of the reactions of unsaturated fatty acids are hydrogenation, where hydrogen is added at the double bond to form a saturated fatty acid. A halogen is added like iodine, bromine, etc. to form halogenated fatty acids. Then there is saponification, formation of soaps. There is oxidation, ozonization and rancidity. This picture depicts hydrogenation, where hydrogen is added to the double bonds of an unsaturated fatty acid to convert them industrially into solid fats by catalytic hydrogenation in the presence of nickel. So, what happens is they become solid, their shelf life is improved and they can be used industrially as shortening agents. Halogenation is similar, where chlorine, bromine, iodine, etc. can be added at the double bonds. This is important in qualitative evaluation of the degree of unsaturation. Oxidation is a reaction of unsaturated fatty acids which are readily oxidized at low temperatures. Saturated fatty acids are more stable. In the first step, dihydroxy products are formed, where in the presence of acetic acid, they are cleaved at the 9th and 10th position of the double bond. You get different types of acids like pelargonic acid, azelaic acid, etc. from oleic acid. Ozonization is when ozone is formed at the double bonds. When it is added to oleic acid, the complex decomposes in water, giving two types of aldehydes and two types of acids. Autooxidation is when some types of lipids and fatty acids on exposure to air form different types of oxidized compounds like peroxides, enidiols, ketohydroxides, epoxides and mole oxides. An example is linseed oil, which is present in paints which dries on exposure to air. In the box, when it is sealed, it is liquid, but once you paint on the walls, it dries because of this property of autooxidation. The rancidity is when a fat or an oil spoils because its fatty acids are being degraded in two types of rancidity: hydrolytic rancidity and oxidative rancidity. When lipid rich foods are exposed too long to oxygen in air, they spoil and become rancid, and they develop an unpleasant taste and smell associated with rancidity, resulting from oxidative cleavage of the double bonds. The fatty acid breaks down into hydrocarbons, ketones, aldehydes and epoxides. Some of the chemical constants like specific gravity, melting point, refractive index, saponification number, iodine number and acetyl value are used for identification of fats and oils. Now, we spoke about triglycerides, which are the simplest lipids constructed from fatty acids, and they are esters of glycerol with 3 fatty acids. Some of them contain the same type of fatty acids on all 3 positions. They are simple triacyl glycerols, and some of them contain different types of fatty acids on all 3 positions. These are more naturally occurring. They occur in all stored oils, that is in oil seeds of many types of plants providing energy. These oil seeds, when they are extracted, they become a fat or an oil which we humans consume for energy. In the body, the fats and oils are stored as adipose tissue. They provide fuel or energy, giving 9 kilocalories per gram. Many foods contain triacyl glycerols or fatty acids, but each type of oil or fat that we consume is different from the other because of the difference in the types of fatty acids esterified to glycerol. Vegetable oils like corn and olive oil are composed largely of triacyl glycerols with unsaturated fatty acids, and thus they are liquids at room temperature. But butter, ghee, vanaspati etc., which contain saturated fatty acids, are solids at room temperature. This table gives a picture of different fats and oils and their fatty acid compositions. These you can study at your leisure, but what is evident from this is lard, butter, animal fats contain more of saturated fatty acids, and therefore, they are hard or they are fats. Whereas, vegetable fats like coconut oil, which contain high amount of saturated fatty acid, is again solid and harder at room temperature. Palm oil is the next, contains 50% saturated and 50% unsaturated, and therefore, it is partly solid and partly liquid. Starting from cottonseed oil, wheat germ oil, soya oil, sunflower oil, safflower oil, rapeseed oil, canola oil, corn oil, all these are liquids at room temperature because they have large amounts of unsaturated fatty acid. Waxes are present in fats. They are esters of higher fatty acids, more than 30 carbons, and the alcohol can be any other alcohol apart from glycerol. They form protective coatings of skins of fruits and plants and also insects. They are used in the manufacture of polishes, lubricants, candles and ointments when they are separated or extracted from natural compounds. Now, coming to phospholipids, we have glycerophospholipids, where very similar to triacyl glycerols, you have a glycerol molecule esterified not to 3, but to 2 fatty acids, and on the third carbon you have a phosphate group attached to another nitrogenous base or an alcohol. So, this is a phospholipid with 2 fatty acids, one saturated, one unsaturated, both attached to the first and second carbon of glycerol, and a phosphate group attached to the third carbon of glycerol with a nitrogenous constituent. This nitrogenous constituent can be any one of these compounds that are shown in this table, like ethanolamine, choline, inositol, serine, etc. Galactolipids or sulfolipids. Galactolipids come under the class of carbohydrates attached to lipids. They are also called glycolipids. You have a glycerol, 2 fatty acids, a mono or a disaccharide and a sulfate group. They are most abundant in membrane lipids in the biosphere, and plant membranes also contain sulfolipids, in which sulfonated glucose residue is joined to a diacyl glycerol in a glycosidic linkage. In sulfolipids, the sulfonate on the head group bears a fixed negative charge like that of the phosphate group in phospholipids. This picture shows you a glucose or a galactose molecule attached to the third carbon of glycerol and 2 fatty acids. Here you have a disaccharide where there are 2 galactose molecules attached to the third carbon along with 2 fatty acids on the first and second carbon. This is a sulfolipid where you have a sulfate group esterified to the 6th carbon of the galactose. Then you have sphingolipids, which are called sphingolipids because the alcohol here is not glycerol, but it is a sphingosine molecule. It is a longer chain alcohol, a very long chain alcohol. The whole chain is shown in a L-shaped manner, and a fatty acid is attached to one of the carbons and a mono or a disaccharide to the other carbons. If there is a phosphate group attached, it is a phosphosphingolipid. Then you have derived lipids like sterols. Sterols bring to your mind cholesterol, which is the major animal sterol, the only sterol present in the animal system. Plants do not have the capacity to synthesize cholesterol. So, no vegetable oils will contain cholesterol because all vegetable oils are derived from plants, whereas all animal fats and animal sources of fats like egg, meat, fish, lard, etc., butter, ghee, all of them contain cholesterol. Some of the plant sterols are stigmasterol, ergosterol, etc. The structure of cholesterol is having a typical steroid nucleus consisting of 3 fused rings with 6 carbons and 1 with a 5 carbon. The steroid nucleus is almost planar and is relatively rigid. The fused rings do not allow rotation about the carbon-carbon bonds. You can see the structure of cholesterol over here. A, B, C, D denote the 4 rings. A, B, C are 6 membered rings and D is a 5 membered ring, and you have a tail consisting of a number of CH2s and a Y shaped molecule at the end. At the third carbon you have an OH group, which is where a fatty acid can be esterified to form cholesterol esters, which are the stored forms of cholesterol and fatty acids in the body. Other derived lipids are present in the chloroplasts of plants or the mitochondria, and these are examples like chlorophyll and carotenoids, and you also have specialized lipids such as those derived from lipids of the plasma membrane or the fat soluble vitamins A, D, E, K. These are some of the structures of the carotenoids. If you break down beta carotene at the extreme left into 2 molecules, you can get vitamin A. Vitamins E and K also have similar structures. Then you have vitamin D, which is similar to cholesterol because it is also derived from cholesterol. Vitamin D can be synthesized from cholesterol within the body. You have ubiquinone and plastoquinone, which are part of the electron transport chain and the photosynthetic cycle. This is a typical fluid mosaic model of the cell membrane containing phospholipids. The blue colored balls are the phosphate groups. The tails, yellow tails, are the fatty acids. So, the phosphate group on the third position of glycerol is more polar, indicated by the blue balls, and the pink transmembrane structures which are coiled are the transmembrane proteins present in cell membranes. To summarize, lipids can be more formally defined as substances such as a fat, oil or a wax that dissolves in organic solvents but not in water. They are a group of naturally occurring molecules that include fats, waxes, sterols, fat soluble vitamins, phospholipids and others, and they are mostly classified based on their structure, physical properties, polarity and their essentiality. Complex lipids are classified into phospholipids and non-phosphorylated lipids. Among phospholipids and non-phosphorylated lipids, you have sphingolipids, which have a sphingosine instead of a glycerol as the alcohol. Among non-phosphorylated lipids, you have glycolipids, sulfolipids and gangliosides. Derived lipids include fatty acids, glycerol, steroids and other alcohols, hydrocarbons, lipid soluble vitamins and hormones. I hope you have understood all about lipids and their classification, properties and structures.